Okay, this week I'd like to devote lecture time to discussing this sort of problem of deriving an approximate, excuse me, approximate two-dimensional model for the elastic plastic deformations of thin plates. So this is a problem in structural mechanics. And a slightly more general version of this discussion would be the case of thin shells, which are, say, curved in some reference configuration. We could discuss that if we had more time, but the main ideas are well illustrated by confining attention to plates that are initially flat in a reference configuration, or take a reference configuration in which the plate is flat. The idea is analogous to what we do in beam theory. Everybody knows about beam theory. Beam theory, the idea is you have a thin prismatic body, let's say, excuse me, and you exploit the thinness of the domain relative to its overall length to derive an approximate one-dimensional theory, right? The one dimension being the axis, say the x-axis along the, say, the center line of the beam. And then that becomes the domain of the problem. The computational domain becomes one-dimensional. So the motivation of beam theory is to go from a very difficult three-dimensional problem to an approximate one-dimensional problem, which is far more tractable. And the price you pay is you've lost some of the accuracy vis-a-vis three-dimensional theory, but you have a very useful analytical tool, but much more tractable tool than the three-dimensional theory will afford you. So I want to discuss the same kind of thing for plates, thin plates. So here's a representative plate. Let's say it's flat. Here's a perspective view. If you look from the top, you see this, say, irregular shape. Let's suppose the plate has a thickness h, and just for convenience, we'll take it to be uniform, although we don't have to. And the basic premise is that that thickness h is very small compared to any characteristic span-wise dimension. We'll call it L. So let's let L be the smallest span-wise dimension, the smallest span-wise length that you can fit into the plate. That could be, if there's an interior hole, for example, it could be the radius of that hole. The idea is that h is much smaller than any span-wise dimension, and therefore much smaller than the smallest span-wise dimension. Okay, so we'll assume that ratio is very small. And then the objective is to derive an approximate two-dimensional model based on this strong inequality. To make things convenient, we might as well take this span-wise dimension L to be the unit of length. So we'll say that L is equal to 1. And then H will be dimensionless, and we'll suppose then that that's much less than 1 in accordance with this assumption. So the idea is to extract an approximate, start from three-dimensional theory and extract an approximate two-dimensional theory in the limit, valid in the limit as h gets very small compared to 1. So if we look at the plate edge on, let's say, here's an edge view, we can orient the plate by specifying a normal, say k, the three direction, and let's let zeta be a coordinate through the thickness. You can call it z if you prefer. And let's single out the midplane of this edge-on view of the plate. Okay, so let be omega will be a midplane. That would be analogous in the case of a beam to the x-axis along the line of centroids of the beam, let's say. And ultimately, we're going to extract the theory which has this omega, this two-dimensional plane, as the domain of the problem, the computational domain. So the idea is to find a two-dimensional theory that furnishes an optimal approximation to the three-dimensional problem in the limit as thickness gets very small. So let's look again at an edgewise view. Here's omega. Here's the normal to omega, k, unit vector k. We can locate any position, the position of any point in the body, three-dimensional position, say capital X. This is our reference configuration then. Capital X we can write as a part projected onto the plane, call it U, and then a part orthogonal to the plane, which would be zeta along k. So U is no longer denoting displacement. It's just the two-dimensional, the projection of position onto the plane. So it's a two-dimensional position. So you take your point in the three-dimensional body, project it to the plane along the normal k. That point has position U on the plane, okay? So we can decompose the three-dimensional position as an in-plane part and a part along k at a distance zeta from the midplane. And so zeta, with omega, the midplane then, zeta runs from the bottom where it's equal to minus h over 2, h is the thickness, to the top where zeta is equal to plus h over 2, okay? Okay, so let's see, how are we going to get a theory that's that involves h? Well, the obvious way to do this is to recall what we did some time ago, way back on page 23, which is the first couple of lectures in the semester. When we were talking about elasticity, we indicated that equilibrium states minimize the potential energy in the case of a conservative problem, or in the case of a non-conservative, a general non-conservative problem, equilibria are such as to satisfy the virtual work or virtual power statement, which is essentially the weak form of the equilibrium equation, okay? So if we're looking at equilibria, this would be a natural thing to do. The potential energy, of course, involves an integral of the strain energy, among other things, over the entire domain. And therefore, the potential energy will contain the thickness explicitly. And so the easiest course of action is to estimate the expression for the potential energy for small thickness, and then render that approximate expression for the potential energy stationary, or minimize it, to get the equilibrium equations, the approximate equilibrium equations that we seek, okay? So I hope this will become clear in the course of the lecture. So as an example, we talked about some time ago dead loading. Let's just focus on this just to show how the idea works. Of course, dead loading is far from the most general kind of loading, but you can conceive of more general types of loading. So let's look at the example of dead loading. Let's suppose the plate is dead loaded on its edge. So we have a traction distribution along the edge, or part of the edge, right? And let's suppose that the top and the bottom surfaces here and here are traction free. Just as an example, of course, we can easily generalize that. Under these conditions, the potential energy we talked about some months ago, that's the integral, if you recall, of the strain energy, subtract the load potential, which for dead loading looks like this, and d kappa n here is a subset of the traction portion of the boundary, which is also a subset of the edge. So I'm using the n subscript to denote what we would call a natural boundary condition. And so d kappa n is a portion of the edge of the plate where we specify traction, okay? And I'm going to use tildes on top to designate three-dimensional quantities. Okay. Later on, variables appearing without the tilde will denote the values of those quantities on the midplane, which are then functions only of the two-dimensional position u. Okay. So just to get things started, I'll use I'll use a tilde for three-dimensional quantities, which is what we start with, and then later on for quantities for the restriction of those quantities to the midplane, where z equals 0, those quantities become functions only of 2D position u, and I'll drop the tilde notation at that point. So for example, the strain energy, let's say the plastic deformation is fixed. Remember, the referential strain energy is 1 over the determinant of K times this strain energy per unit, quote, intermediate volume, unquote, even though there's no intermediate volume. And that depends on H, which is F times K. And if K is fixed, then this becomes essentially a standard elasticity problem for a non-uniform material, in which the energy has an explicit x dependence due to the fact that K has an explicit x dependence. Okay, so let's keep that in mind. So if we regard K as fixed, then the idea would be minimize this energy with respect to the deformation. F tilde is the gradient of the deformation. Once we minimize the energy with respect to this, that is, we solve the equilibrium problem to find the deformation, now we know the deformation chi associated with that fixed K field. Then we know all the stresses and so on. What we could do then, with that deformation known and at that K field, we could solve the flow rule to update the K field or the plastic deformation G tilde. Say incrementally if you're forward integrating in time, numerically, this information then can be used to solve the flow rule to update the plastic deformation at the next time step. Knowing that new value of the plastic deformation, we can freeze it and again minimize the energy to get the new value of the deformation and repeat the process as long as we want, right? As long as the plastic deformation continues to evolve. Okay, so we would call this an incremental minimization problem. So you predict a value of plastic deformation, or you specify its initial value, minimize the energy to find the deformation associated with that plastic deformation. Now you can forward integrate the flow rule, find a new value of the plastic deformation, minimize the energy again to find the new deformation, and just repeat the process ad infinitum. So we would call this an incremental minimization problem. The increment is due to the fact that we're incrementing the plastic deformation by forward integrating the flow rule. Okay. So the procedure then entails rendering the potential energy stationary with respect to the deformation, because when the potential energy is stationary, that's also known as the principle of virtual work or virtual power, or the weak form of the equilibrium equations. That's the necessary and sufficient condition that the deformation satisfies equilibrium. And again, the motivation behind this is that the potential energy, being a global quantity involving an integration over the entire domain, that involves the thickness explicitly. And so we could estimate the potential energy for small thickness, get an approximate expression for the potential energy, and then render that stationary to get the equilibrium equations for the thin plate that we're looking for. Is that more or less clear what the objective is? Okay. And that will give us the equilibrium equations for a thin plastically deformed plate, okay, associated with a given value of plastic deformation. So for example, if you just look at the strain energy, the part of the potential energy involving the strain energy, so I'll call it a calligraphic S here. is the volume integral of the three-dimensional referential energy density. I can write that dV as a dA on the plane, the midplane, times d zeta through thickness, and then carry out the integration with respect to zeta. And then when I'm done, integrate over omega to get the total strain energy. So you see here, this is the place then where the strain energy, the overall global strain energy, explicitly involves the thickness of the plate. So the idea is to estimate this interior integral for small h, okay? So as a prelude to that, let's consider a generic function f of x, three-dimensional function of three-dimensional position, capital X. Write cap x as u, two-dimensional position on omega, plus zeta k. K is fixed, right? The variables here are u and zeta. So this becomes some function of u and zeta. Right? As you move around in the three-dimensional body, it's u that changes and zeta changes, k never changes. So it's the functional dependence is on u and zeta. So I'll call that f hat u and zeta. And the idea is we want to integrate that through the thickness as indicated here in the strain energy. And here in this interior integral, we're integrating on zeta at a fixed value of u. And then when we're done, we integrate with respect to u over the plane omega. So let's fix u on omega. And this integral then defines a function only of h associated with it. I could put a subscript u to indicate that we fix the value of u, but maybe that's too much notation. So this defines a function of h, this integral, and we want to estimate it for small h. Well, that suggests that we use a Taylor expansion. This is a function of h. Let's expand it in powers of h using a Taylor expansion. This integral I at any h is I at 0. We're expanding about, we're looking for small h, an estimate for small h, so it makes sense to expand about h equals 0. The next term, of course, I at 0 is just 0 because the integration limits then collapse to 0. The next term would be h times the derivative of I with respect to h evaluated at h equals 0, and so on, half h squared, second derivative at h equals 0. 1 over 3 factorial h cubed, triple derivative with respect to h at 0. And then higher order terms, small o of h cubed, terms that tend to 0 faster than h cubed does as h tends to 0. Okay, so this procedure requires that we take a derivative of I with respect to h. In other words, we take a derivative of the integral with respect to the limits, right? And that there's a well-known rule to handle that called the Leibniz Rule, which I'm sure you've heard about and long since forgotten. How to differentiate an integral when the limits depend on the variable that you're differentiating with respect to. So for example, d dx, integral a of x to b of x, say of some function f of t dt. The Leibniz rule says that that's just f evaluated at the upper limit times the derivative of the upper limit with respect to x minus f evaluated at the lower limit times the derivative of the lower limit. And that's exactly the situation we have here. Of course, if x were included explicitly in the integral, then you'd have another term which would be the integral of the derivative of f with respect to x in addition to these terms. Okay, has everybody heard of Leibniz rule? I guess that's a no.
Yeah.
Of course, yeah, okay. So the first order of business is take a derivative of I with respect to h. H is involved only in the limits of integration. So we evaluate the integrand at the upper limit. Then we take a derivative of the upper limit with respect to h, which is just 1/2. Then we subtract the integrand at the lower limit. The derivative of the lower limit with respect to h is minus 1/2, which cancels the minus here. So you have this. Now you have the first derivative with respect to h. You can simply go through and take further derivatives. The next derivative would be the derivative of f with respect to its argument. I'll say the prime means a derivative with respect to the second argument, zeta, times the derivative of the argument with respect to h, which is another 1/2, combined, that gives you a quarter. And then here you have the minus a half coming from this. So you have that. And you keep going. You generate, say, a third derivative, where the double prime means a second derivative with respect to the second argument. Okay? Okay. So you immediately deduce then, if you evaluate these at 0, well, first of all, I at 0 is 0, as we said. We need I prime evaluated at 0. That's just f at u comma 0 plus f at u comma 0 times a half, which is f at u comma 0, right? And so on. The second derivative at h equals 0 will be 0 because of the minus sign. The third derivative will be 1/4 f hat double prime at zeta equals 0. Put that in the expression for I of h, the integral, and you get the quadratic term disappears because the I prime is gone, right? And we have the leading order term is of order h, so we get the integrand evaluated at the midplane, and 1/24 because we have a 1/6 in the Taylor expansion combined with 1/4, h cubed, the second derivative with respect to zeta evaluated at the midplane, plus the higher order terms. So this is the idea we'll use to, this gives you then a small h approximation to the integral. And that's what we'll use, say, in the strain energy, this interior integral with respect to zeta. So we can immediately appropriate the result we just had to estimate this interior integral. That'll be something plus small o h cubed, where that something is exactly the same here. It's h times the energy evaluated at the midplane. See, without the tilde now. So psi is the psi tilde evaluated at zeta equals 0, plus 1/24 h cubed, the second derivative of the energy evaluated at the midplane. The second derivative with respect to zeta, the through thickness coordinate, evaluated at the midplane. Okay, so again, I dropped the tilde here. So this notation means. And then we have an error of order small o of h cubed. Okay. Okay, so now the issue is to write this, say, in terms of our strain energy function that we're using in this theory. Psi is 1 over the determinant of k evaluated at the midplane times the three-dimensional w evaluated for when h is on the midplane. So h tilde on the midplane, I'll just call it h without the tilde. H is the elastic deformation on the midplane. The first derivative would give you this. You can easily, these are all midplane values. The prime means, again, a zeta derivative evaluated on the midplane. Okay. So I'll let you confirm these formulas. You just, the obvious thing to do, take a further derivative and evaluate on the midplane. We need the second derivative, and that's a bit more complicated. That involves our w, second derivative on the with respect to zeta on the midplane, and some other complication, a first order derivative, w itself, and then jk complicates matters. These terms are of less relevance because, say, for plastic incompressibility, jk, let's say, is fixed at the value 1. If the initial plastic deformation is k equals the identity, let's say, then the typical flow rule will give you that jk never changes from the value 1 throughout the body, and therefore the through thickness derivatives would all be identically 0 throughout the body, because jk would be identically 1 throughout the body. But we can keep the general situation for now. So then this u that we talked about here, So that's the order h cubed approximation to this integral. So that's, when we put it in here, that's going to give us an estimate of the strain energy per unit area of the midplane. That u, if we take the jk factor to the other side, jku is this somewhat messy expression, an order h term, 1 times w, the jk factor, then order h cubed terms, okay? So it looks a bit unpleasant, but it will simplify things dramatically shortly. Okay, the W again we're talking about, take the three-dimensional energy and evaluate it for H on the midplane. Okay, H is the midplane value of the elastic deformation. W prime, well, using the chain rule, that would be dW dH inner product H prime. But now we're evaluating on the midplane, so the argument of dW dH is just H evaluated on the midplane, and then H prime is the through thickness derivative of H evaluated on the midplane. Do the same for a second derivative, W double prime, which we need here. We use the chain rule again, and that W only depends on zeta implicitly through H tilde, right? So that'd be two derivatives of W with respect to H. That's a function of H, but now we substitute the midplane value in the argument of this function times H prime again, but we already have an H prime, and then we have to differentiate this term. So we have dW dH evaluated on the midplane. Inner product, the second derivative of H on the midplane. Okay, well, so H and all these H prime and so on, these involve the deformation gradient F and the plastic deformation, right? So the idea of what we're pursuing is to fix the field K tilde of capital X. That means K on the midplane is known, and its through thickness derivative is a known function also, as well as its second through thickness derivative. And those all are involved here. So H is Fk, H prime obviously is this. These are midplane values. H double prime is this. Just take a further derivative. So the theory then requires that we know K on the midplane, K prime, that's the through thickness derivative of K evaluated on the midplane, and its second through thickness derivative. And it also calls for the deformation gradient evaluated on the midplane, its through thickness derivative, and its second through thickness derivative. Okay, so we'll work on that, but in the meantime, we now have an estimate of the strain energy, the three-dimensional strain energy, calligraphic S, is ordinary S plus terms of order small o h cubed, where ordinary S is this, right? That's the leading order, or the order h cubed approximation to the strain energy, which now involves only an integration over the midplane. And the argument here then is the approximate value of the strain energy per unit area of the midplane, valid to order h cubed. And it's a function only of u, the midplane position, vector u. Okay? So we need to do some work then to fill in the details, because to specify this, we need to work out all these, therefore we need to work out H prime, H double prime, and so on. So we have a bit of work ahead of us to do that. So this is a typical feature of all structural theories in which the domain of the problem is less than 3 dimensions. For example, beam theory is 1-dimensional. The mathematics, once you have the theory, are much easier because you're replacing a 3D problem by a 1D problem in the case of a beam. But the theory has to have more structure. There's additional structure in the theory to compensate for the reduction in the dimension of the problem, right? And so that's the additional structure that we're pursuing here. Okay, so let's look at the deformation gradient. It's a 3-dimensional function, right? Function, I'll call f tilde of x. Replace x by u plus zeta k, and there should be a closed parenthesis here where my cursor is. Sorry for that. So then this is, we'll call it f hat of u and zeta, as we did before, except now, of course, this is a tensor, deformation gradient. So this just reminds you of what it is. It's the referential gradient of chi. Chi of x we can also write as a function of u and zeta. I'll call it chi hat. So these are all three-dimensional variables. I want to get an expression for the deformation gradient on the midplane, evaluated on the midplane, as well as its through thickness derivatives evaluated on the midplane. So let's remember that f dx is d chi by the chain rule. Dx I'll write as du plus k d zeta, k is fixed. D chi, however, that involves the variables, the variables are u and zeta in this function. So d chi would be a two-dimensional gradient on the plane. I'll use this symbol, operating on du, but then a through thickness derivative, prime, times d zeta, right? So this two-dimensional gradient of this three-dimensional position field will look like this. There should be a hat on here. In terms of Cartesian components, this would be chi I comma alpha, alpha running from 1 to 2, ei tensor product e alpha. So that involves this matrix, chi I comma alpha, I runs from 1 to 3, alpha from 1 to 2. That's a 3 by 2 matrix. So that's a 3 by 2 submatrix of the 3 by 3 deformation gradient. Okay. So I'd like to compare both sides of this equation and read off an expression for f. Let's notice that du, that's just a change of u in the plane. I can write that as a projection times itself. So this thing 1 here is not the shifter anymore. I'm going to appropriate that notation now for something else, which is the projection operator onto the midplane. The projection is three-dimensional identity minus k tensor product k, where k is the normal to the midplane. Okay, so u is entirely u is a vector in the plane. Du is also in the plane, so it's equal to its own projection, and that will help me to figure out what f has to be by comparing both sides here. So I can write du as 1 du, where 1 is this projection, again not the shifter. Okay. And I'll write, so I'll group terms this way. Then we have f hat 1 all on du. And then I have f operating on k d zeta is two-dimensional gradient of chi du plus chi prime d zeta. Now this f1 business, the projection is the same as e alpha tensor product e alpha, where e1 and e2 is an orthonormal basis, and e1 cross e2 is k. So e1, e2, and k is a right-handed orthonormal basis, let's say. And the projection is just e alpha, tensor product e alpha. That's just the identity operation on the plane itself, the two-dimensional identity. And f e alpha, on the other hand, if you write f in this Cartesian representation, mixed basis representation, and then take that and operate on e alpha, you'll just pick up f sub I alpha, ei tensor product e alpha. So this is a 3 by 2 matrix, which will match up with this 3 by 2 matrix ultimately. Okay. So this equation has to be true for all choices of du and d zeta. For example, for d zeta equal to 0, so you're on a fixed level, zeta equal constant, then the remaining part of the equation would be valid for all du, which means that f hat 1 is equal to this 2d gradient. With that, we have then the remaining content of the equation is fk d zeta is equal to chi prime d zeta for all d zeta, so fk is chi prime. With that, we can reconstruct the three-dimensional deformation gradient. We can write it as itself times the three-dimensional identity. Write the identity as the projection plus k tensor product k. Then group terms like this, f1, which we know, plus fk tensor product k. That gives us this representation of the three-dimensional deformation gradient in terms of a two-dimensional gradient of position on the plane plus a part through the thickness, a three-dimensional derivative tensor product k. This is a vector, of course, tensor product k, whereas this is a tensor. Okay. The procedure we outlined so far also calls for the through thickness derivative of f. That's now easy. So this is a derivative with respect to u in plane position, whereas the prime is a derivative with respect to zeta, and the zeta derivative of grad chi will be the grad of the zeta derivative of chi, right? We can interchange the roles of the partial derivatives, assuming sufficient continuity. We can interchange the order of the differentiation. That's what we've done here. And then we have just to differentiate this term again with respect to zeta. And then we need to do it again, so we have this, okay? And the theory requires us to evaluate all these quantities at the midplane where zeta equals 0. So for example, when zeta equals 0, the deformation itself becomes a function only of u. Let's call it r of u. So r of u gives us the deformation of points on the midplane. We also require chi prime evaluated at the midplane. That becomes a function of u. Let's call it d of u. Notice that chi in the midplane and its zeta derivative evaluated at the midplane have nothing to do with each other, right? So think of chi as a function of zeta. Its value at zeta equals 0 and its derivative at zeta equals 0 don't have anything to do with each other, right? They're completely unrelated to each other. It's just over an interval of zeta values. Of course, chi prime is the derivative of chi. But if you evaluate it at one point, namely zeta equals 0, they can be quite independent of each other, right? The same is true of the second through thickness derivative evaluated at the midplane. That's a function of u. We'll call it g of u. It's a vector g of u. The third order through thickness derivative evaluated at the midplane, we'll call it h of u. And these are entirely distinct vector fields defined on the midplane. That we can, to give some interpretation of what they mean, we can use them to construct a Taylor expansion of the three-dimensional position as a function of zeta. That would be, we can expand about zeta equals 0. The lead term would then be r of u. The next term would be zeta times the derivative evaluated at zeta equals 0, namely d of u, and so on. Half zeta squared, the second derivative at zeta equals 0, that's g of u, and so on. So this gives, the vectors r, d, g, and h give you the small zeta expansion of the three-dimensional position in the vicinity of the midplane. And zeta is bounded between minus h over 2 and plus h over 2, which are both very small for a thin plate, right? So zeta is always going to be close to 0 in this physically. Okay, so this gives you, the RU gives you the midplane deformation, DU gives you the slope with respect to zeta through the thickness. This gives you kind of curvature, the second derivative through the thickness, and so on. Okay, so we can now evaluate f on the midplane, f tilde or f hat on the midplane, where zeta equals 0. That was grad chi hat at zeta equals 0, in other words, grad r. And then the through thickness derivative on the midplane was d. So we get f on the midplane in terms of the midplane, the 2D gradient of the midplane deformation and its through thickness derivative. The prime of that evaluated in the midplane would just be grad d plus g tensor product k. the second derivative on the midplane would be grad G plus H tensor product K, and so on. And grad R, just as we had before, it's the 2D gradient of this three-dimensional deformed position of the midplane. It would be Ri comma alpha EI tensor product E alpha, 3x2 matrix. So these are all, everything with a grad in front is a 3x2, can be associated with 3x2 matrix. Okay, let's give some physical interpretation of some of these variables. Let's say here's our reference configuration, and you have an edge-on view of the plate. Here's the midplane. Here's the normal. And let's just draw a scratch through the thickness, right? So let's imagine a material curve, vertical material curve, material line, directed along the unit vector k, extending from minus h over 2 to plus h over 2. So this is a material curve, and we know from continuum mechanics what happens to a material curve after deformation. It gets mapped by the deformation gradient into a new vector. If we evaluate that operation on the midplane, where f tilde is equal to f, then according to this equation, f on k, right, this grad r on k is 0 because E alpha dot k is 0. We just get this on k, which is d. So d is the midplane value of this material curve vector after deformation. Okay, so here's the material curve prior to deformation. Here it is after three-dimensional deformation. It goes like this. We don't know anything about it yet. Say a general curve like so. We know the tangent to that curve is going to be aligned with fk, so d is the tangent to that curve at the midplane. At the mid-surface. The mid-surface here is also a material surface, so it gets deformed into this surface. Let's call it curved surface, call it small omega, which is just the image of the midplane under the deformation. D then gives you the direction of that curve, or the tangent to it, as well as a stretch. You know, this could be a stretched curve at what was the midplane, which is now over here. We can also use the Piola-Nansen formula to figure out the normal, right? Remember, f star the cofactor f star operating on the initial normal gives you the final normal to a material surface. Well, this material surface is now over here. The normal looks like this. And alpha is the areal stretch, which is the norm of f star k. So you've all seen the Piola-Nansen formula before. Okay. And by the way, in classical plate theory, an assumption is made, an assumption that goes back to ideas of Kirchhoff and Bernoulli before him in terms of beam theory. You've all heard of the notion that in a beam, when you bend a beam, the plane sections remain plane and perpendicular to the center line, right? In this context, that would be the assumption that this material curve remains normal to the deformed mid-surface. By the way, omega need not be equidistant between these two extreme surfaces anymore, right? That's true over here, but after deformation, there could be some squashing, right? But the analog of the Bernoulli-Euler hypothesis, or in this context, the Kirchhoff hypothesis, would be that D remains aligned with N. But there's no a priori reason why that should be true, right? Because F on K in general is not parallel to F star K, because F and F star are entirely different tensors, right? So we'll just see what the theory tells us. We're not going to invoke any assumptions. We'll just use the apparatus of the theory to figure out the relationship between this D and the normal. We will not invoke any assumptions. So standard treatments, by the way, of plate theory do invoke that assumption a priori, but that seems to be quite an ad hoc assumption, and there's no real logical reason to impose it apart from making things simple. But one should not make things too simple, right? Maybe you've heard of Einstein's joke, everything should be as simple as possible, but not simpler. Right? So invoking Kirchhoff-Love hypothesis or Bernoulli-Euler in the context of beams would be making things simpler than they should be. Okay, so we've so far analyzed the, by the way, we could, a similar interpretation of the vector field G, right? That's the second derivative with respect to zeta through the thickness. So that gives you information about the curvature of this material curve, right? And then H of U gives you higher order third derivative information. So not only are we, so the assumption that the cross section remains plane, or this line remains straight after deformation, that would be analogous to, I guess, what we call the Timoshenko hypothesis, Timoshenko beam theory. We'll abandon that also. There's no reason to impose that either, right? We might have a curvature of that material line through the thickness. So you may have heard names like Timoshenko beam theory or Mindlin plate theory, that sort of thing, which allow a shear deformation that is D not aligned with N, but still require that this material line remain straight. But we won't even invoke that. It's an improvement over the classical Bernoulli-Euler or Kirchhoff assumption, but it's still too restrictive. Okay. All right, so far we've looked at the strain energy. Let's look at the load potential for the dead load problem. So the boundary where we're applying tractions on the edge, you can think of as a kind of composed of the boundary of the midplane, which is itself a curve, right? And together with the through thickness interval between minus h/2 and h/2. So it's standard to write that as this kind of a product that's called the Cartesian product of these two sets, this interval with this one. And we've indicated, just by way of talking about a specific example, that we're assuming that the top and bottom of the surfaces of the plate are traction free. So we specify traction there, namely 0. So those are portions of the traction part of the boundary. We can easily generalize that, but we're simply trying to illustrate the ideas here. So we'll take the simpler example. So here's our load potential. I'll call it calligraphic L. Okay, and we can break up this surface integral now into an arc length integral around the curve, the boundary of the midplane. So that's S is arc length along that curve. And then a through thickness part. dA on the edge is ds times d zeta, right? This is an area element on the edge of the plate that can be written as ds arc length along the boundary of the midplane times the through thickness d zeta. So that means, again, we're integrating on zeta with respect to from minus h/2 to h/2. We can again write the three-dimensional traction on that surface as a function of u and zeta, right, as usual. And we know how to do that. We know how to estimate this interior integral now using the Taylor expansion and the Leibniz rule. When we do that, we get the leading order, the order h cubed estimate, I'll call it ordinary L, plus an error of size small o h cubed, where ordinary L, I'll call it, so that's the boundary integral over the curve that bounds the plane omega of a function chi, not a vector, a scalar field, ds. And chi works out to be this. You can easily verify that just by following the same procedure. That involves traction evaluated on the edge at the midplane. Everything here is a midplane value. The second through thickness derivative of the traction on the midplane times h cubed. It also involves position of the midplane. It involves this d and g. We can call d and g, we can call them directors if you like. And it involves again, also the first order through thickness derivative of the traction evaluated on the midplane. Okay. You may have heard, in fact, the late Professor Nagdi in this department was a very famous mechanician who did a lot of work on plate and shell theories. And he was famous for developing what's called the director theory of shells and plates, and in which this notion of director that we've just been talking about plays a significant role. Okay. You can read his work if you're interested. So our potential energy then is strain energy minus load potential, the three-dimensional ones. With our approximations then, we have an approximate potential energy valid to order h cubed plus an error, small o h cubed, and that approximate potential energy is our approximate strain energy minus approximate load potential, given here. Okay. Okay, so we have now an energy that depends on the midplane deformation and these additional director fields, B of u, G of u, and H of u, right? So that's a bit of a complication relative to three-dimensional theory, in which you have a potential energy that just depends on one unknown vector field, the deformation, chi, right? Chi hat. Here we have an energy. It's much simpler because we're dealing only with a two-dimensional theory now, but it's got more structure because the energy depends through these integrands on r, the deformation of the midplane, and d, its first order through thickness derivative at the midplane, plus g plus h. So that's what I meant before by the theory having to compensate for the simplification in the reduction of the domain from 3 dimensions to 2, but there's more structure now in the theory. And so the structure of the theory is more complicated, even though from the point of view of solving problems, it's far simpler because you're dealing with a 2-dimensional domain rather than a 3-dimensional one. Okay, well, let's look at a special case associated with pure bending, the so-called pure bending problem. So here's a picture of say a beam, the situation for a beam. And you all know, so you can think of a beam bending as the same as our plate bending problem. If you look edge on the plate and you bend the plate, it looks like you're bending a beam, right? And you all know from elementary beam theory that the elastic solution would involve, in pure bending, there's no axial loading along the axis of the beam, just pure bending moments. Pure bending involves a linear variation of stress through the thickness, and the stress is 0 on the central line of the beam, which is analogous here to the midplane of the plate. And if you have yielding, right, so this is a uniaxial stress through the distribution, varies linearly through the thickness. Of course, if you have yielding, say a perfectly plastic material, then that stress cannot go above the yield value, so it saturates at a yield value, and you have a stress profile that looks something like this. And you can find nice pictures like this in, say, the book by Kachanov, for example, which you have access to. Okay. So let's have a look at the theory for pure bending, which is simpler than the general theory, which involves stretching and bending at the same time. So the pure bending entails the notion that the stress is 0 then on the midplane. So in particular, our Piola stress evaluated at the midplane would be 0. The Piola stress is based on the reference configuration, right? Kappa, I'm calling it kappa. Whereas this object here, dw dh, is the Piola stress based on the so-called intermediate configuration. And if you look way back in your notes, pages 64 and 65, dW dH evaluated on the midplane, that would be the midplane Piola stress times the cofactor of the inverse plastic deformation, K star. And that's also equal to H times the second Piola-Kirchhoff stress based on the intermediate configuration, referred to the intermediate configuration. Okay, so that's theory that we've had some time ago. So with P equals 0 then, on the midplane, this is a special case of the general theory, then the midplane value of the second Piola-Kirchhoff stress, again, relative to the intermediate configuration, right, would be 0. Because that's 0 and H is invertible, so S is 0. And remember our constitutive equation for the stress was that S equals the classical tensor of elastic moduli times operating on the elastic strain, E. And remember, C is positive definite under our assumptions, so it's invertible. So this implies that the elastic strain is 0 on the midplane in the case of pure bending, okay? But it's only 0 on the midplane. Of course, it's not 0 off the midplane in the case of pure bending. So that means, so remember, E is a half H transpose H minus identity, so that means H transpose H is the identity, which means H is a rotation. It's equal to the rotation factor in its polar decomposition. The stretch factor is equal to the identity. Okay, so under in the case of pure bending, the midplane value of the elastic deformation is a rotation field. It's not uniform. It doesn't have to be uniform rotation. If H were a gradient, which it's not, then it would be uniform. Remember, in continuum mechanics, you know that if the deformation gradient F is a rotation, then because F is actually a gradient of a vector field, that means you can prove that it has to be a uniform rotation. That's what gives you rigid body dynamics. Uniform, the rotation is uniformly distributed throughout the body. Here, H, recall, is not the gradient of any vector field. So although it's a rotation, it need not be uniform. Okay, so remember our constitutive assumption. The strain energy was a half E inner product CE. E is 0 when H is rotation, so the strain energy is 0 at the midplane. Its through thickness derivative, which we need in setting up the theory, is this by the chain rule, where we evaluate dW dH when H is a rotation. Here it is. When H is rotation, S is 0, so dW dH is 0 when H is a rotation, inner product H prime. So this is 0. It doesn't matter what H prime is, you still get 0. So that means that very complicated expression for the approximate strain energy per unit area of the midplane. Remember, we had all those terms on the right-hand side here. It just boils down to this W double prime term with an H cubed over 24 in front. If you look back, let's see, here. W is 0 on the midplane, W prime is 0, we just get this last term here. Okay, so that's a drastic simplification, and all those complicated K prime terms, JK and JK prime, are irrelevant now in the case of pure bending. On the other hand, the W double prime from that chain rule representation we had is the second derivative of W evaluated when H equals R, operating on H prime, inner product H prime, and then we had this other H double prime term, which gets multiplied by dW dH when H equals R, which is, again, is 0. So we just have this term. So the approximate strain energy valid to order H cubed, then, there's no order H term anymore because that was associated with W, which is 0 on the midplane. The leading order term is of order H cubed now. And that's just this H prime inner product, all this stuff. We can simplify this. If you look way back on page 66 of the course notes, we had a formula, I'm copying verbatim. Two derivatives of w with respect to h evaluated at any rotation q operating on any tensor A is that rotation times our classical moduli operating on Q transpose A. So we can use that here to write W double prime is H prime inner product. Here we have an R instead of a Q, so it's R, C, R transpose H prime. And we can clean this up a bit also, just by using the rule that, say, we have a tensor, call it A dot another tensor B times a third tensor. This fourth order tensor on a second order tensor is itself a second order tensor. We'll call it C. That's trace AC transpose B transpose from the definition of the inner product. You can interchange the factors at will. Well, you can put the factors in the back and front. So we could put the B transpose in front. We have this. Then this would be B transpose A inner product C. So we could write this. We could take B, put a transpose on it, put it in front. H prime inner product C, R transpose H prime, which is a more symmetric looking version of the result. So here's our leading order approximation to the strain energy in the case of pure bending. Now here we've approximated H by R, right? H is a rotation under the pure bending assumption. That's still H, and H involves F and K. And H prime also involves F and K, F prime and K prime. So the plastic deformation is embedded in this formula. Okay. As far as the load potential is concerned, well, there's no Piola stress on the midplane. So that means the traction on the edge, which would be the traction right there on the edge of the midplane, that would be the midplane Piola stress times the normal to that edge, right? That would be 0. And so here's a plan view. You're looking down. Here's the normal, and so on. So with P equals 0, the integrand in the approximate expression for the low potential, we called it chi, simplifies dramatically. We just get this. And it's also of order h cubed. And then remember, there's an error, small o h cubed involved, which I'm not making explicit here. So our approximate potential energy then starts out at order h cubed. We can divide it by h cubed, and what we're left with is this 1 over 24 times all this stuff, the strain energy part, and the approximate load potential. And I'm carrying the 2 here. This was a 1 over 12 before, so I need the 2 here. Okay. And here, so now we have this approximate energy, potential energy of the edge-loaded plate. Okay, here's our 3-dimensional traction. Remember, on the edge, on the edge, the surface, prismatic surface of the plate. We can write that as a function of u and zeta. In the dead load problem, this is an assigned function. It doesn't change with the deformation, right? So it's fixed on this portion of the boundary in the dead load problem. You take its derivative with respect to zeta, first and second derivatives evaluated on the midplane. Those are also assigned functions of now u on the edge, and therefore assigned functions of arc length on the edge, because the edge is given in parametric form by specifying u as a function of s. So these become known functions, fixed, independent of deformation on the edge in the dead load problem. So this, apart from the h cubed term, is our ordinary L, load potential. When we take a variation of that, in the sense of the calculus of variations that we talked about at the beginning of the course, I'll specify a variation with using a superposed dot. So all the terms involving P are fixed. They're independent of how you vary the deformation. You get an r dot, which is like a virtual velocity of the midplane, and a d dot, which is like, tells you how that vector d, that material curve, changes its length and its orientation. So this, I'm pausing to discuss this because this then would be so from mechanics we know that anything that has is power conjugate multiplies a velocity must be a force, right? So this is a force, like a force density. And this is multiplying d dot, which involves also a change in orientation of d, like a rotation. That should be like a moment density, right? And in elementary beam theory, maybe you remember that the shear traction on a cross-section is parabolic, a parabolic distribution through the thickness, right? And a parabola is determined by the second derivative with respect to the through thickness coordinate at any point, let's say on the midplane. So this p double prime plays a role analogous to that. It's analogous to the classical, it accounts for the classical parabolic shear stress distribution on a cross-section in the analogous beam problem. Whereas p prime, that would tell you the slope of the traction, or the, that would give you the linear part of the variation of the traction. That gives rise to a bending moment, right? The linear variation of stress through the thickness generates an overall bending moment. So these terms are entirely familiar and expected from the analogous beam bending problem, okay? But something also nice happens here. In the case of pure bending, all the order h terms in the potential energy disappear identically. So the actual three-dimensional energy is E plus small o h cubed, remember. If you divide that by h cubed, see E over h cubed here, we have an expression for it. The right-hand side doesn't involve h at all. If you take the limit of this as h goes to 0, this disappears. Small o h cubed goes to 0 faster than h cubed as h tends to 0. So this E over h cubed is exactly the limit at small h of the actual three-dimensional potential energy over h cubed. What this means is that this E that we've derived is the rigorous leading order approximation to the potential energy for small h, right? Because the smaller h gets, the closer E gets to epsilon, the exact three-dimensional potential energy. So that's encouraging. That means the theory we're deriving gets better and better the smaller the thickness is, in the case of pure bending. See, in the case where we're not confining attention to pure bending, we also have an order h term here. And if we divide that by h cubed, we're going to get 1 over h squared, which blows up, right, as h goes to 0. So in that case, the leading order problem would be of order h. We call that the membrane problem. The order h cubed, if the leading order problem is order h cubed, that's associated with pure bending. But you can be confident that the theory we're deriving here becomes more and more accurate from this result, the smaller the plate thickness becomes, okay? So you would expect that the two-dimensional theory becomes a better and better approximation to the exact three-dimensional problem as the thickness of the plate tends to 0. Okay. So it further means that since our task was to minimize the exact three-dimensional energy, and we're looking for deformations that accomplish that task, then for the smaller the plate thickness is, that's equivalent to minimizing our approximate potential energy. Okay? So our task, we can achieve our task, which is to find the deformation that minimizes the actual three-dimensional potential energy We can accomplish that task to a high degree of accuracy by minimizing the two-dimensional potential energy that we've just derived. So minimizers of the actual energy and the approximate energy coincide in the limit of small thickness. Okay, and it's a much easier job to minimize this, notwithstanding the extra structure in the theory, because this is a two-dimensional problem rather than a three-dimensional one. Another way of saying this is that the three-dimensional problem in the limit of small h actually becomes a two-dimensional problem to leading order. Right? Of course, you can't make a plate have zero thickness, but the smaller the thickness is, the smaller these error terms become, and your approximation gets better and better. Okay. Okay, so let's see what we can do in the remaining few minutes. Let's have a look at the kinematics that we've set up. We have a midplane deformation, we have the d field through thickness derivative, g, and so on. Let's see what we can say about those. Here's our decomposition of F, elastic and plastic parts. H is a rotation under the pure bending scenario, which means that the actual Cauchy-Green deformation is just G transpose G, right? At the midplane. This is all at the midplane. And G, of course, is the inverse of K. And here's the midplane value of F. Maybe we can use this to get some information about this D, this D field that we talked about. Let's notice now that grad R, that's a map from the midplane, the initial midplane, to the tangent plane of the deformed surface, the deformed midplane, at a given material point P. So here's your material point with position U. Grad R maps vectors in this plane to vectors in the tangent plane to the deformed image of that midplane, small omega. Okay, you can easily verify that. You could grad R has components, say R comma 1 and R comma 2. So if you use 1 and 2, x1 and x2 as convected coordinates, then the R comma 1 after deformation would be tangential to the surface, and R comma 2 would be tangential. So grad R would map vectors in the plane to vectors in this tangent plane. Okay. So that means, well, we can always decompose D in the following way. D can have a part along n, as we saw in the sketch previously. In fact, under the Kirchhoff assumption, very restrictive, D would be equal to n. That's overly restrictive. Because grad R takes any vector here in the initial midplane, two-dimensional vector, and maps it to this tangent plane, grad RE for E, an arbitrary vector in the initial plane, would be an arbitrary vector in the tangent plane. And then with E arbitrary, that gives you an expression for the tangential part of D, which we don't know. And the normal part would then just be D dot n along n. Right? So we can always write, without any loss of generality, this D field as a part along the normal plus grad R times some arbitrary two-dimensional vector in the initial plane. Okay. Let's see, we know something about n from Nansen, the Piola-Nansen formula. Alpha is the areal stretch. Recall that the cofactor of F, if you've taken continuum mechanics, or if you haven't seen this formula before, you can find it in Chadwick's book, a very nice introductory book on continuum mechanics. The salient feature of the cofactor is that it operates on the cross product of two vectors in this way. It gives you F on A crossed with F on B, where A and B are arbitrary vectors. That's useful in deriving expression for the determinant, say the determinant of F. if you've seen Chadwick's book, for example, or ME 185 in this department, you know that's the determinant is take any right-handed orthonormal basis, say E1, E2, and K. That's the so-called scalar triplet product or box product of FE1, FE2, FK, divided by the box product of E1, E2, and K, which is 1 because we're choosing these to be right-handed orthonormal. The box product is, say, this cross that dot that, right? So we get this formula for the determinant. According to this, that's the cofactor operating on E1 cross E2, which is K, dotted with FK. And that's kind of handy because F star K, according to the Peele-Nansen formula, is this areal stretch alpha times the normal to the deformed midplane. So the determinant of F is alpha, which is the norm of F star K and hence positive, dotted with FK, which is D. So we want the determinant of F to be positive, so that means N dot D has to be positive. In other words, so D dot N must be positive, and we'll make essential use of that fact momentarily. Okay, so a moment ago we had D transpose G, the plastic deformation, is F transpose F because H is a rotation at the midplane. F looks like this. Let's put its transpose in front and carry through the product. We get this. Okay, we get a grad trans. So this looks like a kind of Cauchy-Green deformation at the midplane. Then we have grad R transpose D, tensor product K. K tensor product D, grad R, the same as putting the grad R transpose in front of the D in the tensor product. Then we have D dot D, norm D squared, K tensor product K. So let's figure out these terms. Well, grad R maps omega to the tangent plane of the deformed midplane at the material point P, right? That tangent plane depends on which material point you're talking about because it's a curved, the surface is curved, so the tangent plane varies from point to point. The transpose then does the reverse. It maps that tangent plane back to omega. So vectors in the tangent plane, it operates on vectors in the tangent plane and maps them back to the midplane, the initial midplane. D involves an N. Here's the decomposition of D. Grad R transpose, N is perpendicular to that tangent plane. So it gets annihilated by grad R transpose. This gives you a 0. And you're just left with grad R transpose grad R. We'll call that C, small c, because its structure is exactly the same as the Cauchy-Green deformation, capital C. Here it is in components. You write out grad R, do this operation. You get this component form. Sum on I from 1 to 3, alpha and beta run from 1 to 2. At the end of the sum on I, you get a 2 by 2 matrix. So that's like a 2 by 2 Cauchy-Green deformation pertaining to the midplane. And with that definition of C and this result, you go through here and you get the 3-dimensional Cauchy-Green deformation evaluated in the midplane is this 2 by 2 part, C, E, tensor product K. These are like transverse shear terms. This is in the initial plane. This is perpendicular, so this is like a transverse shear. And then you have a 3-dimensional, a through thickness squashing term, stretch term here. And the C is a 2 by 2 tensor. All of this is controlled by the fixed value of the plastic deformation. Okay. Now we're out of time, so let me just finish this page and then we'll come back next time. We can assert that this small c is actually positive definite. Take any vector A in the initial midplane, 2-dimensional, then operate on it with the deformation gradient. Because F has non-zero determinant, this vector will be non-zero, so its squared norm is strictly positive. That's the same as FA dot FA, which is A dot F transpose FA. If you operate this on A from the right, A is two-dimensional. It kills off the K terms. You have a term here, kills off this term, and you get a CA plus a term here. Then dot multiply on the left with the same A, you're going to kill off the K term again, and you'll just get this. So this is a positive definite two-dimensional tensor. If you look at this expression then, and operate on the right with this projection we introduced before, that'll kill off all the K terms. Operate on the left with the same projection, that'll kill off the remaining K term on the left, and you'll just pick up the C term. So your C will be the projection, F transpose F projection, but that's also G transpose G. So C is controlled by the plastic deformation entirely. It's fixed by the plastic deformation in the case of pure bending. That is, we're not stretching the midplane, right? It's beyond what the stretch induced by plastic deformation. If we operate this now on K, right, both sides of the equation on K, you'll pick up a term here, get nothing from here, nothing here, and you'll get a d squared K term, okay? So you get this, project it onto the plane using the projection operator, you get just CE survives, projection on K is 0, and you get this. Now you can, because C is invertible, you can solve for that E term. C was controlled by the plastic deformation, and then you see that so is E, that part of the director D you've been looking for. And then now you can dot the equation through by K to kill this part. It gives you norm D squared is K dot this, which is this. So norm D is norm GK. So the length of the director is also controlled by plastic deformation alone in the case of pure bending. So these are both determined by this. If we go back to the director itself using this formula, this term is orthogonal to this term, right? This lives in the tangent plane, this lives in the normal direction. So by Pythagoras Theorem, the squared norm of this is the d dot n squared plus this squared, right? Which is E dot, this two-dimensional Cauchy green times E. So we can solve for d dot n. We have this, we have to take the positive square root because d dot n has to be positive from our earlier result. So this too is determined by the plastic deformation entirely. Okay. And on the other hand, from Nansen, Piola and Nansen is just this. From the properties of the cofactor, that's the same as FE1 cross FE2. FE1 is simply grad RE1 because it kills the D term. D tensor product K on E1 is 0. You just get grad RE1 cross grad RE2. So alpha n is controlled entirely by grad R, which we don't know yet. Alpha itself, on the other hand, because F star is RG, all star, and the cofactor of product is the product of the cofactors in the same order, and R is a rotation, so it's equal to its own cofactor. You get this. Take the norm of that. The norm is insensitive to the rotation. You just get this. Alpha is determined by the plastic deformation. N is determined by the plastic deformation then, and by grad R. So ultimately, put everything together in this formula for D. B is actually a function of the shape of the deformed midplane. In other words, it's a function of grad R, two-dimensional gradient of R, three-dimensional R, and the plastic deformation. Some function that we can figure out. We just figured it out, essentially. By the way, in the case of pure elasticity, with pure bending, pure elasticity means there's no plastic deformation, say G is the identity, so H is equal to F. The entire deformation gradient is elastic. if you go back upstairs here with G equal to the identity, you get C equal just the projection, two-dimensional identity. Identity on K would be K, project that, you get 0, so E would be 0. G identity means norm D equals K and so on. So you get a big reduction. You get this, you get equal 0, you get this. D dot N will equal to 1 then, according to this formula we just derived. And that means D would be equal to the normal. That recovers the famous Kirchhoff assumption or the Bernoulli-Euler assumption that D is aligned with the normal, in fact, equal to the normal, right? That's true in the case of pure bending, we rigorously derived it. In the case where there's no plasticity. Plastic deformation, however, alters that scenario and destroys the Bernoulli-Euler hypothesis. So quite often, I'm way over time here, you will see people developing plasticity theories for plates based on the Bernoulli-Euler or Kirchhoff hypothesis a priori. They're just not accurate, right? You introduce unnecessary errors when you do that. Okay, so let's continue this next time. Sorry to drag this on too long. We'll complete the theory next time. And if there are no questions, then I'll stop here.